A breakthrough for scientists after they had a 20-minute conversation with a humpback whale.
An animal bigger than a school bus with perhaps the most sophisticated form of communication that has ever existed.
A researcher at MIT freezes as the final results appear on her monitor. For several long seconds, nobody in the lab says a word. Then she quietly breaks the silence. This changes everything. An artificial intelligence system has just finished analyzing more than 9,000 recordings of sperm whale conversations. Everyone expected patterns, nobody expected language. Buried inside millions of underwater clicks, the AI has uncovered something astonishing. A hidden phonetic system with vowel-like sounds that mirror the very building blocks of human speech. Not something vaguely similar, something so structurally alike that even the researchers struggle to explain what they're seeing. For decades, scientists believed sperm whales communicated using a small collection of simple click patterns, each carrying a fixed meaning. That theory stood unchallenged for years. Then one AI model looked deeper. What it discovered didn't simply improve our understanding of whales. It shattered one of biology's oldest assumptions and raised an unsettling question. What if humanity has been sharing this planet with another species that possesses the foundations of language, and we only realized it now? Before we uncover how this AI made one of the most astonishing discoveries in modern science, take a second to subscribe. The turning point arrived almost by accident. David Gruber was sitting quietly in his office at Harvard University's Radcliffe Institute, listening through a pair of headphones to recordings he had collected while studying jellyfish in the Caribbean. Mixed among those recordings were the familiar clicks of sperm whales. He had heard them countless times before. To him, they were simply part of the background, rapid bursts of mechanical sound that reminded him of underwater Morse code, but never seemed important enough to investigate further. Then someone happened to walk past his open office door. MIT cryptographer Shafi Goldwasser paused for a moment after hearing the strange clicking sounds drifting into the hallway. She stepped inside, listened carefully, and immediately noticed something everyone else had overlooked. "That sounds like Morse code," she said. "Have you tried using machine learning to decode it?" The question caught Gruber completely off guard. He hadn't. In fact, no one had. Goldwasser wasn't asking out of simple curiosity. Throughout her career, she had specialized in breaking encrypted communication systems, the same kinds of codes governments rely on to protect their most closely guarded secrets. Years of searching for hidden patterns had trained her mind to recognize structure where others heard only noise. To her ears, the whale clicks weren't random sounds. They sounded like an encrypted language waiting for someone to crack it. That single conversation changed everything. Soon another expert joined the discussion. Artificial intelligence researcher Michael Bronstein explained that the same deep learning technology, capable of powering advanced language models like ChatGPT, could also be used to analyze animal communication. The challenge wasn't the algorithms, it was the data. If researchers could gather enough recordings and enough behavioral context, the AI might eventually discover patterns that humans had never been able to see. The idea quickly grew into something far bigger than anyone had imagined. Researchers began planning a project unlike anything marine biology had ever attempted. Over the next 5 years, teams of AI specialists, roboticists, linguists, and marine biologists would combine their expertise with one ambitious objective: to use the most advanced technology available in an effort to communicate with another intelligent species. Achieving that goal would require collecting more whale recordings than any scientist had ever assembled, documenting more behavioral context than any previous study had attempted, and applying levels of computing power never before used in marine biology. By 2020, that vision had become reality. The project was officially launched as Project CETI, the Cetacean Translation Initiative. Supported by the TED Audacious Project and backed by researchers from MIT, Harvard, UC Berkeley, and 15 other institutions, the team established a permanent research station in the Caribbean nation of Dominica. The location was chosen for a reason. For decades, scientists had observed the same sperm whale families returning to those waters year after year. Individual whales were already known by name. Their family trees had been carefully documented. Researchers knew which females served as matriarchs, understood the relationships between generations, and had mapped the social structure of entire whale clans through years of patient observation at the ocean's surface. But simply watching whales was no longer enough. The researchers wanted to understand what the whales were actually saying. To accomplish that, they built one of the most sophisticated listening systems ever placed in the ocean. Hydrophone arrays were permanently installed along whale migration routes, allowing conversations to be recorded across enormous stretches of sea. At the same time, harmless suction cup biologger tags were attached to individual whales. Each tag carried 3 synchronized microphones capable of separating the voices of different whales, even while several of them communicated simultaneously. The equipment didn't stop there. Every tag also recorded GPS position, diving depth, body orientation, and tiny movements measured to fractions of a degree. Nothing was left to chance. The researchers wanted to know not only what each whale was saying, but exactly who it was speaking to, what it was doing physically at that precise moment, and what every surrounding whale was communicating at the same time. Every piece of context that could possibly reveal meaning was collected together. That had always been the real objective. The goal was never simply to record sounds. It was to build enough contextual information that, one day, the language itself might finally become understandable. Years of work eventually produced an extraordinary collection. More than 9,000 sperm whale recordings were gathered and fed into the same class of deep learning artificial intelligence that powers modern, large language models. The sounds surprised almost everyone who heard them. They didn't resemble the long, haunting whale songs most people imagine. Instead, they sounded remarkably like streams of digital information being transmitted beneath the ocean. Then, the AI finished its analysis. The results didn't simply challenge existing knowledge, they rewrote it. For decades, scientists believed sperm whales communicated using about 21 different codas. The AI found 156. Yet the number itself wasn't the real discovery. What truly mattered was the hidden structure inside every coda. Each communication contained changes in tempo, shifts in rhythm, and tiny ornamentation clicks arranged in recurring patterns. Those variations weren't random decoration. They served a purpose. They behaved exactly the way phonemes function in human language, small modular building blocks that combine according to rules, creating meanings that no single sound could express by itself. Suddenly, the old picture of whale communication disappeared. The whales weren't selecting messages from a fixed list of 156 signals. They were building new messages dynamically from a reusable phonetic system. It was the same fundamental architecture found in every known human language. One comparison made the discovery easier to understand. English creates millions of different words using only 44 basic speech sounds. Remove one sound, and thousands of words disappear. Introduce new rules for combining sounds, and entirely new words become possible. The AI suggested sperm whales operate in remarkably similar fashion. Their clicks form a limited acoustic inventory, their communication follows grammatical rules. And together, those rules generate an almost limitless range of possible expressions. Researchers were no longer looking at isolated animal calls. They were staring at the framework of a genuine communication system whose full complexity had remained hidden for decades. When Dr. Daniela Rus from MIT described the findings publicly, her words sounded almost restrained. Our results show there is much more complexity here than previously believed. This is challenging the current state of the art of beliefs about the animal world. Yet behind that calm statement lay one of the biggest scientific surprises in modern biology. Nothing the AI uncovered represented a small correction to existing knowledge. Instead, it demolished one of science's oldest assumptions, that only humans had ever independently evolved the structural foundations of language. The evidence now suggested otherwise. Somewhere beneath the darkness of the ocean, nearly a mile below the surface, another species had been using that kind of communication for roughly 30 million years. Humanity had simply never known how to listen. Just when the researchers believed they had uncovered the biggest surprise hidden inside the whale recordings, another scientist decided to look even closer. At the University of California, Berkeley, linguist Gaspar Bacos approached the data from an entirely different direction. Rather than studying complete coda sequences the way everyone else had, he focused on something much smaller. Using some of the most advanced phonetics equipment available, he examined the acoustic properties of each individual click at the highest resolution modern science could achieve. No one expected that decision to change everything again. As the analysis unfolded, the results became impossible to ignore. Hidden inside those clicks were patterns that looked astonishingly familiar. The whales weren't simply producing clicks. They were producing vowel-like sounds. Bacos identified acoustic structures resembling the ah sound heard in the word father, the e sound heard in see, and even diphthongs, the gliding combinations of two vowel sounds, like the oi in boy. For decades, vowels had been considered one of the defining features of human speech. Now they were appearing in the communication system of an animal living nearly a mile beneath the ocean's surface. After reviewing the evidence, Bacos and his colleagues reached a remarkable conclusion. We concluded that this spectral pattern, basically a whole new dimension in their communication system, is meaningful. That statement carried extraordinary weight. Vowels are not simple sounds that appear by accident. Producing them requires precise control over frequency, specialized vocal anatomy, carefully coordinated muscles, and the neurological ability to manipulate those sounds intentionally. For generations, scientists believed that combination belonged exclusively to humans. It was thought to be the product of millions of years of evolution unique to our own lineage. Yet here was evidence suggesting another species had arrived at something remarkably similar. Bacos later explained the discovery in simple terms. In the past, researchers thought of whale communication as a kind of Morse code, but this paper shows their calls are more like very, very slow vowels. This suggests a complexity that approaches human language. That sentence forced researchers to confront an uncomfortable reality. These whales had developed their communication system in a world completely unlike ours. They evolved in darkness. They navigated through sound instead of sight. Their ancestors had separated from ours hundreds of millions of years ago. There had been no shared path toward language, and yet both species appeared to have reached strikingly similar solutions. When scientists considered the biology behind that discovery, the implications became even more extraordinary. The human vocal tract evolved over millions of years. A lowered larynx, specialized tongue muscles, and precise airflow control gradually transformed simple sounds into spoken language. Human beings evolved toward vowels. Sperm whales followed an entirely different evolutionary path. Their communication grew out of echolocation clicks inside an underwater world, where tiny differences in high-frequency sound could determine whether they found food or went hungry. Their environment demanded precision for survival. Yet despite beginning from completely different origins, both lineages appeared to arrive at communication systems that looked functionally alike. That wasn't coincidence. It was an example of convergent evolution, two unrelated branches of life independently arriving at the same complex solution. For many researchers, that realization changed the question entirely. Perhaps vowel-based communication wasn't a strange accident unique to human anatomy. Perhaps it was something intelligence naturally discovers whenever it becomes advanced enough. For centuries, humanity believed that language, with its vowels, phonemes, grammar, and contextual flexibility, was the final dividing line separating human cognition from every other living creature. The sperm whale alphabet didn't merely blur that line, it erased the ground beneath it. And yet, an even greater surprise was still waiting. Discovering that whales possessed the structural pieces of language was remarkable. Learning how they actually used those pieces proved even more astonishing. One researcher recalled the first time he truly listened to sperm whales. "I became interested in sperm whales when I heard their sounds. They sounded like they were coming from another universe, a siren song being broadcast from the darkest reaches of the sea." As Project CETI continued analyzing years of recordings, another pattern gradually emerged. The same whale never communicated exactly the same way twice. Its codas changed depending on which family member it was addressing. They changed depending on what another whale had just communicated. They even changed according to events unfolding around the group at that exact moment. This wasn't a rigid signal system with predetermined responses. It was communication adapting continuously to context. The whales appeared to choose different vocal patterns depending on social situations, much like humans naturally speak differently to children than to colleagues, or soften their words depending on who is listening. That kind of flexibility lies at the heart of pragmatic language. Years of field observations supported the growing evidence. Marine biologist Shane Jarrow had spent 13 years living alongside sperm whale families in the waters surrounding Dominica. Day after day, he watched their interactions unfold. Eventually, the behavior became difficult to interpret any other way. It is hard not to see cousins playing while chatting, to not see a mother hand her calf to a babysitter and exchange what looks, for all the world, like a few parting words before diving deep to hunt. The conversations themselves were extraordinary. Some lasted nearly an hour. Several whales often communicated at once, responding to one another, overlapping, and building upon previous exchanges. Researchers documented measurable conversational timing, recognizable rhythm, and clear turn-taking between speakers. Occasionally, two whales clicked over one another at the same time. Instead of disrupting the interaction, those interruptions appeared perfectly acceptable within sperm whale society, much like family members interrupting each other during a familiar conversation. The deeper scientists looked, the more those underwater exchanges resembled something they had never expected to find. Not isolated calls, not instinctive signals, but the living rhythm of an ongoing conversation. The deeper the researchers looked into the recordings, the more one unsettling question refused to go away. What kind of brain could actually do this? Producing the right coda wasn't simply a matter of making sounds. A whale had to choose the right sequence for the right individual at precisely the right moment. That required far more than memory or the ability to control sound. It required something scientists call theory of mind, the ability to recognize that another individual has thoughts, knowledge, and perspectives different from your own, and then adjust your communication accordingly. For generations, That ability had been considered one of humanity's defining traits. Now, the evidence was beginning to suggest otherwise. As researchers continued analyzing thousands of whale conversations, subtle social patterns gradually emerged from the data. Some whales consistently dominated conversations, others spoke less often. Certain exchanges resembled disagreements, while others sounded remarkably similar to reassurance or comfort. Some conversations occurred only between particular family members, while others appeared to involve an entire whale family communicating together. Even more remarkably, the social relationships researchers had spent decades documenting at the ocean's surface matched the communication patterns being measured beneath it. The conversations were not random. They reflected relationships. Behind those conversations stood the largest brains found anywhere in the animal kingdom. A sperm whale's brain weighs roughly 6 times more than a human brain. Those enormous brains support equally extraordinary societies. Sperm whales live in matrilineal families stretching across multiple generations. Grandmothers pass knowledge to daughters, daughters pass it to calves, and cultural traditions survive for decades. Together they coordinate deep-water hunting expeditions in complete darkness, hundreds of meters beneath the surface. Hunts that simply could not succeed without continuous communication between multiple individuals. Researchers had begun to realize that such behavior required something much richer than simple signals. As one scientist explained, sperm whales communicate before they hunt and when they socialize, so we think that there might be more meaning to their communication system. The truth was becoming impossible to ignore. These had never been simple animals. Science simply hadn't been listening carefully enough. Yet despite everything the AI had revealed, the researchers remained careful not to overstate their conclusions. The system had uncovered the structure of the language. It had not translated a single word. That distinction mattered. The phonetic inventory had been identified. The grammatical rules behind the clicks had been modeled. The vowel-like sounds had been catalogued. Individual whales could now be recognized by their unique acoustic signatures, while years of recordings had revealed consistent conversational patterns between family members. Every one of those discoveries had been carefully verified and peer-reviewed. But one enormous mystery remained untouched. Nobody yet knew what any of the conversations actually meant. What message was hidden inside a particular coda? Why did one sequence speed up while another slowed down? What was a mother telling her calf during those long exchanges before a dive? What changed when the family matriarch addressed the entire group? Those questions still had no answers. Researchers realized they had learned the grammar of a language without understanding a single sentence.